I will begin. Let me begin with a word of prayer. Heavenly Father, we thank you for this day. Again, I thank you for this class and this time we have to study your creation. Just pray that you be glorified in what we do this day, Lord. In your name I pray, Lord Jesus. Amen. All right, so let us take a look at Maxwell's equations and so forth. We need to think a bit about Ampere's law. So here's a problem we can think about. Suppose you've got like a parallel plate capacitor, right? And like this, right? And you've got a current that's coming in like this, all right? And suppose that this is a non-constant current, right? Then what can happen if we think about drawing Ampere's law, Amperian loop here, like this, right? So, we can talk about this S. So we'd have what? Like the integral over the boundary of S of B dot dl, dr, right? dl, yeah, is equal to mu naught times I enclosed, right? And the current enclosed there would be I, right? But the thing is, in this situation, I could imagine, instead of doing like that, I could imagine, what if I was to, I don't know, say, bubble this out like this, right? So notice that, let me call this thing T. So here, the boundary of S is common to the boundary of T, right? But if we look at the integral of the current density over T, right? What would that be? Like, what's the current that's going through T? Notice that I've purposely put T so that it's over between the capacitor plates where no charge is flowing, right? So what's the charge per unit area time there flowing? What's the current density? Well, it's nothing, right? So this, which is by definition the current enclosed by T, is 0, right? Yet this is of course equal to the integral over the boundary of T of B dot dl, right? I mean, these are the same set of points, right? So what gives? I mean, how can this be? And see, that's the kind of, like, a non-constant current can create this situation, right? You can have a non-constant current which is building up the charge on the capacitor plate like this, right? It's totally possible. So what you see is that Ampere's law cannot hold for non-steady currents, right? The point of this thought experiment is that Ampere's law fails in its naive form for non-constant currents. Put another way, Ampere's law, as we've learned it already, is really only for the magnetostatic case, right? The case of constant magnetic fields. But if the current is not constant, you know, the magnetic field is going to also be variable, right? Because the magnetic current is proportional, the magnetic field is proportional to the current, according to the rules we've looked at, Biot-Savart law and all that. And so the magnetic field is going to be changing as well, right? So this is not a constant magnetic field. It's not the, this is, you know, not magnetostatic case, all right? So what gives? So, well, let's think about this. So the electric field is getting built up here, right, between these plates. And so the idea that was invented by Maxwell is to think of the electric field that's also changing, right? He said, oh, wait a minute, maybe a changing electric field, we should think of that as a sort of current, actually, right? It's kind of like a current to have a changing electric field there. So with that thought, if we generalize our notion past physical currents to also include these other kinds of currents that are coming from electric fields changing, then maybe we can repair Ampere's law. All right. So let me show you how that goes. So what we do, following Maxwell, so this is Maxwell's suggested form. It's correct form of Ampere's law. Goes like this. We have the integral over the boundary of the surface, B dot dl, all right, in circulation of the magnetic field, and it's going to be equal to mu naught times the current through S plus mu naught times what he calls the displacement current. Which isn't really a physical current. So let me just give you the formulas here. So I sub S is equal to the integral of J dot dA. Oh, I'm sorry. I can't remember which class I'm in, guys. We use dA in here, don't we? Anyway, so I just meant surface area element. So this is the actual physical current that's piercing S, right? But then the displacement current, I sub D, is defined to be the integral over S, like I said, having to do with the change in the electric field. So partial E, partial T dot dA. So this is the so-called displacement current right here. And then the counterexample I'm showing you no longer is a counterexample. See, because what happens is, okay, so yeah, the current through S is changing, right? But guess what? So is the displacement current. So when I change from the S surface to the T surface, I don't face a logical contradiction because I still have a non-trivial displacement current through the black bubble. So like the displacement current through S might be 0, whereas the physical current's non-zero, whereas through the black one, the opposite's true. The physical current is 0, the displacement current's non-zero because the electric field's changing between the plates. All right, this is the idea. And it turns out to be correct. So if we put this all together, what we now have is that the integral, it's a closed integral, so integral over the boundary of S of B dot dl, let me clean things up a bit here, it's equal to mu naught times, well, the integral over S of, let's see here, we've got J plus epsilon naught partial E partial T dot dA. But let me remind you that we have Stokes' theorem, which hopefully by now in your Calculus 3 class you've talked about Stokes' theorem, right? No?
Just finished grades. And you're also missing a parenthesis.
Missing a parenthesis. Why I never.
Sure.
There you go. So, thank you. So, who do I need to poke? Are we talking Dr. Wang? He will get to it. Don't worry. We still got time. There's still class time left, right? So, and that's an everyday week, every day of the week. So you got a whole week. You should get to Stokes' theorem next week. I hope. You better get the Stokes' theorem. Anyway, so you're going to get to it in here. So this is equal to the integral over S of the curl of B dot dA. All right?
Yes.
Oh, he has talked about it. All right.
But I don't think mine. I know Smith.
Yeah. Oh, Smith has? Well, good. Schmidt, yeah. Yeah, do we have a Smith? We used to have a Smith. This is also confusing for me. But the thing is, if this is true, right? If this is equal to this for arbitrary surfaces, well, this reveals that there's also a fundamental differential relation between the curl of the magnetic field and this right over here. Mu naught times J plus epsilon naught partial E partial T. So this right here is Ampere's law. With Maxwell's correction. All right. So let us collect the thoughts. Let's write down all of Maxwell's equations, all of them, right? Here they are. So we have the curl of B is mu naught. That J is the current density, right? We do take the surface integral of that over the surface to get the net current through a surface. That's what that is. It's current per unit area. So epsilon naught mu naught partial E partial T. All right. I just multiplied it through this time. We also have the divergence of the electric field is rho over epsilon naught, right? We have the divergence of the magnetic field is 0, and we have the curl of E is equal to minus partial B partial T. These collectively are called Maxwell's equations. And in a nutshell, this is electromagnetism is simply the study of how to solve these equations. All right? So let me just rho is dq dv, right? And J is the current per unit area. Now, you guys, for the most part, I think are engineers, right? So sometimes engineers will call these the microscopic field equations. So you might take a fields and waves course, then you'll talk about something called the displacement and something called the induction, perhaps. You use H. So basically E gets replaced with something called D, and B gets replaced with something called H, right? The D and the H fields, they reflect the study of electromagnetism and matter, all right? That's beyond this course. I don't talk about it just except to mention that at the basic level, we think about electric and magnetic fields. These are the so-called microscopic equations. At least that's what Wikipedia says. So, and it seems to have been written by an engineer, so I'll trust it. All right. So what were the names of these equations? I already told you the name of Ampere's law down here. Which is the second one? What was that? Let's just review. This is what? This is Gauss's law. Right? If we take the integral of that and use the divergence theorem, we get the charge enclosed divided by epsilon naught equals to the electric flux like we studied. This, what's this? This is no magnetic monopoles. If you could find a physical situation where you had a magnetic field with non-trivial divergence, that would mean that you had a monopole. And we just haven't observed those. There's an asymmetry, right? There's like a clear asymmetry between electricity and magnetism. See the difference? At least in our physical universe that we're currently inhabiting, it seems like there's electric charge, but there's not magnetic charge. All right. However, the motion of electric charge does create magnetism. And so what's the last one here? What's this called? Nobody? Yes, the curl of the electric field is minus the time rate change of the partial. It's minus the partial derivative of magnetic field with respect to time. That's true. That is mathematically what I wrote there. But what is the name of this? Which dead white guy discovered this? Faraday. Yeah, yeah. This is Faraday's law. Right. All right. So those are Maxwell's equations. And what's interesting is once you write these down, you can put them together. Let me show you some calculations. So there is an identity which you probably did not see in Calculus 3, but this is true. The curl of the curl. Remember that one? Curl of the curl? Well, this, it turns out, is equal to the gradient of the divergence minus the Laplacian, which is the divergence of the divergence of E. I'm not writing this right. My bad. Let me just write it properly. Nabla squared E. Right? So this is a, I mean, forget about E for a second here. Let's just talk about an arbitrary vector field F. This is an identity of vector calculus. So this Nabla squared in Cartesians is partial x squared plus partial y squared plus partial z squared, okay? So this is an identity of vector calculus. Suppose we're in free space with the current equals to 0 and the charge density equals to 0. Okay? In that context, what happens? Well, we have Maxwell's equations, right? So if we look at the curl of the electric field, that is equal to what? We got the gradient. What's the divergence of the electric field? So this is rho over epsilon naught, right? But that's 0, right? That's 0. Then over here we have del cross, what's the curl of the electric field? Faraday's law says that's minus partial B, partial T, right? And apparently that's equal to minus Nabla squared E. So the curl is partial derivatives with respect to your spatial coordinates, x, y, and z, right? And you can commute the order of partial differentiation, right? So this is really the same as minus partial t of the curl of B. What's the curl of B? So I'm commuting the order of partial differentiation there, yeah? That's something you guys learned in Calc 3, I'm pretty sure. Remember that? We can swatch the order of partial derivatives. It's true. So let's see here. Curl of B, mu naught j plus epsilon naught mu naught partial e partial t, right? But what are we assuming about j? We're in free space. There's no current, so j is 0. So this is just minus partial t of mu naught epsilon naught partial E partial t. All right. So there's a minus on both sides, and what this gives us is that the gradient squared, like nabla squared on the electric field, is equal to mu naught epsilon naught partial squared E vector partial t squared, right? Which I could rewrite over here as partial squared E partial t squared. I mean, I guess that's, we can just leave it like that, I suppose. Oh, fine, I'll rewrite it this way. Partial E squared partial t equals to 1 over mu naught epsilon naught nabla squared E. So if we're in, say, one dimension, in one dimension this looks like partial squared, Ex, let's say, partial t squared equals to 1 over mu naught epsilon naught partial squared E sub x partial x squared. I mean, of course, I'm just saying I shouldn't, I mean, this isn't true. I'm sorry, guys. Let me not write down nonsense. This is, of course, still nabla squared Ex. The same is true if I write it down with y or with z, So we have this partial differential equation for the x component, for the y component, and also for the z component. All right, that's what's going on here. So let me remind you something. If we have partial squared y, partial t squared, is equal to 1 over v squared, partial squared y, partial x squared. This is the one-dimensional wave equation. Now, if you took my physics 1, my apology, because I didn't cover this, right? Sometimes I derive this in differential equations, all right? You can derive this by studying Newton's second law on like a little segment of a string under tension, okay? This v is the speed of the wave. Right? So let me just erase the black. This doesn't really help us much. Let me get to that. What does it say? If you compare these two equations, this is also a wave equation. The second derivative with respect to time is proportional to the, the second partial derivative with respect to the spatial direction. This is in fact the three-dimensional wave equation. All right? And what you can see from this is that, E solves a wave equation with speed apparently c equal to what? Oh, wait a minute, did I mess this up? Uh-oh. I got the V on the wrong side. I'm a dummy. Analyze, think about the dimensions here, guys. Like dimensional analysis, I've got like meters over second squared. And over here I've got like meters over meters squared. And this is a meters over second squared. So I've got, this is dimensionally inconsistent, this equation. Long story short, I should have had the, I should put the v squared over here is what I'm what I'm getting at. So I'm sorry, this is, apparently I need to, apparently I need to go teach this in Physics 231 again because I've forgotten my ways.
Does it change the units? Because now you have the velocity squared, so 1 over velocity squared on the other side. Shouldn't that be a sign?
Oh, I think I meant to make this 1 over velocity squared. My bad. I think that would fix it because then I have, this has a 1 over second squared. This has a second squared, so the 1 over second squared and the second squareds cancel. And so both sides have units of like 1 over meters. Like both sides of the equations have dimensions of 1 over length with that modification. That's better. Okay, so with that, oh man, so I should have stuck with that. So we really should compare to this guy over here, right? I'm sorry. Man, this is such a bummer. So I should compare, probably should compare this versus this by analogy, right? So this would these two together would suggest that my velocity for the electric field is what? 1 over the square root of mu naught epsilon naught. See, because I should think about like 1 over v squared is equal to mu naught epsilon naught, which says that v is equal to 1 over the square root of mu naught epsilon naught. Right. Can you guys calculate this for me? What's this equal to? What was that pesky epsilon naught anyway? What was that thing? We got constant 32. Where'd my constant button go? There it is, 32. And then that times 4 times pi times 10 to the what? -7. So that gives me a 1.126 blah, 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 10 to the minus 17. Square root that thing. And then reciprocate that thing. And I get, all right, let's write it down. I got a 299. 2997 92458 meters per second. Or if you like, C is about 2.998 times 10 to the 8th meters per second. You should recognize this number. What is it? This is the speed of light. So what this calculation shows you is that Maxwell's equations imply that if you have electric and magnetic fields, right, that are solutions to Maxwell's equations in the vacuum, that those waves travel at the speed of light. Guess what? They are light. Okay, that is light. That is what light is. Light is an electromagnetic wave. Now, we can also, there's a very similar calculation which shows you that. It is also true that nabla squared b is equal to mu naught epsilon naught partial squared b partial t squared. This turns out is also true through a very similar calculation to the one I shared with you guys. So it's like just a mathematical consequence of Maxwell's equations that light is an electromagnetic wave that travels at the speed of, well, I say at the speed of light, that sounds like a tautology, but it travels at a speed which is governed by what? The permeability and the permittivity of space itself, right? So this is very weird from a perspective of the study of waves in classical mechanics, right? Because like in classical mechanics, the velocity of something might depend on, it would depend on, in part, on the velocity of the source. If I throw a baseball on a train, then the velocity of the baseball on the train is the velocity of the train plus the velocity of the baseball, right? But these equations are essentially implying that the speed of light is this, and what did this have to do about where the source of the light came from? Well, nothing, right? Like, it's got nothing to do with the source. It's just a property of space and time itself, so this implies that the speed of light is constant with respect to all inertial observers. So Einstein's genius was taking that as an axiom for special relativity. But once you do that, you've left the world of Newtonian physics, So perhaps some of you guys will take modern physics with Dr. Budara's. You'll talk more about that in there, I think, So, advertisement. You've heard stories? I think it's got to be fun. I'm guessing. So I'm hoping personally to teach the second course in this stuff, like the higher level physics, electromagnetism, in the fall. And if all goes as I'm hoping, I might end up teaching quantum like next spring. So we've gotten permission to start running these courses next year, ostensibly. I mean, I'm jumping the gun a little bit telling you guys, but spread the word. If you're interested in taking higher level physics past this course, for the first time ever residentially, well, maybe not the first time ever. I think Dr. Skambordis truthfully taught these courses back in the early 90s. All right. Something unfortunate happened in the early 90s with respect to, well, let me not get into the source. Anyway, so something happened and a third of the programs here were cut in like 91 or 92, 93, somewhere in there. The physics minor got cut then. It took some time for us to get it back. But we got it back, and now there's the online physics program, right? And hopefully we're going to start offering hybrid courses. So we've gotten permission to run the online physics program residentially, which is kind of hard to wrap your mind around. But what it basically means is we have permission to teach some of the higher level courses which are offered for the online physics. But we'll be teaching them in the, much less frantic 16-week format, 15-week format, right, residentially. And hopefully we'll have some online students tagging along, assuming that they would rather do, a higher level physics course in 16 as opposed to 8 weeks. I mean, I know I would. But anyway, so there you go. There's an advertisement. Spread it around if you know people who want to take interesting physics next year. Those courses having enrollments would help physics continue. If nobody signs up for those classes, then it will go away. So, all right. Okay, so this is just an amazing story, right? Like, that through correcting Ampere's law, Maxwell opened the door through some relatively simple calculations to see that light is an electromagnetic wave. So there's this beautiful synthesis of electricity and magnetism, and ultimately opening the door to a deeper understanding of what light itself is, right? So if you were to take a course in optics, what you're going to be doing is solving these equations. That's how we understand carefully reflection, refraction, all these things are derived from these equations at their base. Any questions before I go on here?
So you said the theory of relativity presupposes that the speed of light is constant regardless of the frame of reference?
Yeah, the Einstein's theory of special relativity takes as an axiom that the speed of light is constant in all inertial frames of reference. The other axiom is that the laws of physics have the same form in all inertial frames of reference. Of course, this begs the question, what's an inertial frame of reference? But
Fairly self-explanatory.
yeah. So it turns out that means that your notion of time and space has to get mixed, because the inertial, they're called the Lorentz transformations. They mix space and time together. You lose things like simultaneity, for example, in special relativity. If I say that there's 5 seconds between, event A and event B, and you're in a different frame of reference, and you say, well, no, there's 3 seconds between event A and event B, that's totally possible. So you lose the concept of simultaneity, and yet everyone agrees that the speed of light is constant. Yeah. But anyway, that's a whole other course. And if you wanna understand special relativity pretty deeply, I highly recommend. There's about 4 lectures in Shankar's. I think he's from Yale. He's got like popular physics set of lectures. If you watch his 4 lectures on special relativity, you'll get very far. He explains things pretty well in there. I think I have links on my website. Okay, so solution. See, I don't remember this. So I need to tell you some more things. I won't derive these things. I'm just going to tell you them, okay? So some fun facts, basically. So the electric and the magnetic field are perpendicular in the vacuum. So like when you solve these things, you get an electric field that goes one way, and you get a magnetic field which goes like perpendicular to it. It turns out that the magnitude of the electric field is equal to c times the magnitude of the magnetic field, where c is the speed of light. Here's something more interesting that I sometimes test on. You can define something called S, which is 1 over mu naught E cross B. This is the so-called pointing vector, P-O-Y-N-T-I-N-G. Yeah. It points in the direction of the electromagnetic waves going. And you can also calculate the pressure of light, and that, it turns out, is the magnitude of the pointing vector divided by c. I think, to be fussy, people usually talk about taking a time average there, but yeah, I'm not going to be so fussy. So this gives light. So this is like pressure from light wave. Pressure from light. So this would quantify, for example, radiation pressure. All right. In my notes, I have some silly example with a laser pointer. I'm not going to write down. But let's see here if I can tell you anything else for today. So I wanted to show you the equation, at least give you one equation for so okay, like the study of electromagnetic waves obviously is, involved. Like you could spend courses, like several courses, understanding the details here. But man, oh phooey. This is not helping me. Rats. All right. I mean, well, I guess I could hazard a picture here. All right. So I will foolishly attempt a picture. Suppose this is the picture of the So here's a typical electric field, right? And I'm going to make the magnetic field perpendicular to that, and like this, let's say. All right. So let's see here. So for instance, this would be the magnetic field. These are not drawn to scale, right? Notice the scale factor here. Like the electric field's like 10 to the 8th bigger. Yeah. In terms of the system of units we use, you know? Okay, so if that's the story, if you trust me, which direction is this wave going? So we do E cross B, right? The electric field across the magnetic field. So this wave is traveling that way. And if I actually gave you formulas for the electric field and the magnetic field, you could take the cross product of them, and then that would give you the pointing vector, right? And if you were to calculate the magnitude of that and divide by the speed of light, that would give you the radiation pressure. There's something else I was going to tell you guys today. Oh, last time I got hung up on something about the transformers. The answer there was totally stupid. So we derived last time, what was the relation between N1 and E1? Guys, remind me what I wrote down. What was it? What was I had a formula between the voltage on the one coil, the number of turns on the other one, and the current. How did it go? I just worked it out. I don't have it written down anywhere. What? N2 times what? Oh, no, I don't care about flux. I want the formula that relates the number of turns and the current and the voltage. M, yeah, M is equal to what? No. I derived a formula that related M as the ratio of two things that were different. Current, voltage. Say again, N sub 2 what? No flux in the equation I'm looking for. I wrote an equation that had voltage, current, and number of turns, and nothing else. And no flux in this equation.
E1 equals N1.
Ah.
U0, N1, N2, A over L.
Who writes down everything in here?
I write down everything.
You do?
Could be it anywhere here. Over here.
Oh, yeah, that one. So M is E1 over DI1 D2 dt. No, that's not it either.
Mu0, N1, N2, A over L.
No, I don't think so. That one, I think. Oh, man. Ah. I will look at it after class and announce in the problem session. But the point is just this. If you're looking at, if your voltage has the form like E naught, say cosine omega t, something like that. If I look at that equation and I look at what happens, like the cosine terms cancel out, and I'm just left with a relation which just gives me that the voltage in the primary, and it gives me a multiplicative relation between the voltage in and the voltage out, is all I'm saying. Like that, if we apply the case of a sinusoidal voltage source to the equations I had last class, we will get the multiplicative formula for transformers that I was remembering. Anyway, I'll try to fix it in the problem session today. I don't remember at the moment. Oh, one other thing. So this here, there's something else to talk about in terms of energy and frequency and wavelength, but I think we talk about that after the test, so don't worry about that for the test. Maybe the final, but not here.
Oh,